Okay, hello everyone. Uh, Welcome to the second day of the IISBS's annual meeting on research in astronomy. So I hope that you have already enjoyed the meeting till now. We're gonna start the first session with Dr. Mehrdad Mirbabayi from ICTP talking about uptunneling to the CETA. Please go ahead.
Okay, thank you, and thanks to the organizer for inviting me. So yes, I'm going to talk about uptunneling to the CETA based on this relatively recent paper. And the question that I'm going to ask in this talk is that or the setup that we are going to study is to imagine that we have a potential with a true vacuum and a false vacuum. And we live in the true vacuum. And we want to ask whether we can probe the false vacuum, or how well can we probe the false vacuum? If we ask this question in quantum field theory, if there was no gravity, then the answer would be yes, we can probe the false vacuum by carefully preparing some initial state and having patience. So for instance, we can consider the following initial state. If the initial state is one in which there is some big region in the false vacuum. So imagine here is the false vacuum, and then asymptotically we are in the true vacuum. This initial state will decay into asymptotic states of the true vacuum. Now, if we apply time reversal to this process, then by starting from these asymptotic states in the true vacuum, we produce a big region of the false vacuum. And by putting enough energy and spending enough time, we can produce as big region as we want of the false vacuum and study its property. Now, the main goal is to ask the same question in gravity. What happens if we turn on gravity? If we have gravity, then the situation is dramatically different, because if the true vacuum is a Minkowski vacuum with zero cosmological constant, then the false vacuum has positive cosmological constant. And therefore, if we tunnel there and produce or if we produce a big region of the false vacuum with positive CC, then it will inflate. And therefore, it can change the asymptotic structure of the space-time. This is actually a problem, or a similar situation was considered by these authors when you have an inflating region connected via a black hole to the asymptotically Minkowski here, FRW spacetime. So as you can see here, the asymptotic structure has changed when we have this inflating region. It's not just a feature of Minkowski. And this process cannot happen classically because of cannot happen if we start from non-singular initial state, because of the Penrose singularity theorem. So indeed, if we want to have such a situation in which there is this inflating bubble, inflating region of false vacuum connected to the region of true vacuum, then in the past there has to be some singularity. Now, this setup that was considered by these authors was in the context of inflation. So it wasn't Minkowski space in the past, but there was inflation, and the singularity theorems actually apply to the inflationary setup. So inflation is known to be past incomplete. Okay, we want to start from Minkowski. Classically, we cannot do it. because of singularity theorem. So the natural question is that whether quantum mechanically we can probe the false vacuum or produce a big enough region of the false vacuum by a quantum tunnel. Why would we expect this to be the case? Because of the general expectation that quantum mechanics would explore all possibilities. So we want to see if it explored this possibility. And indeed, this is a question that was asked 30 years ago by these authors, in which they consider, so they basically consider this very similar, essentially the same tunneling process. They try to study tunneling from a situation in which you have a small region of false vacuum, which is so small that it will decay. Tunneling from this configuration starting from this configuration to a configuration in which there is a bigger region of the false vacuum that inflates. So there was this question was asked 30 years ago. However, there is no consensus that this solution is actually acceptable. There are some issues with this tunneling solution that was proposed there. So up to now, there are discussions on whether this is a valid process or not. So the problem is still open. Now you might ask, why do I even ask this question? Why do we care about uptunneling to the city, producing this big bubble of false vacuum that inflates? One motivation is just curiosity. This seems to be a well-defined question in the context of quantum gravity, and it's hard to find well-defined questions in this context. So here is one. We should try to understand what is the answer to it. However, another motivation that is perhaps more relevant to this meeting is to wonder about the initial condition of our universe. So let us think about the situation that led to the discovery of inflation. At that time, physicists were trying to ask about what happened before the hot Big Bang. And this question, asking what happened before the hot Big Bang, led to the discovery of this interesting and very simple model that explains a lot of the structures that we see in our universe. And this is a model that is fully based on the physics that we know and we understand. Field theory, effective field theory coupled to gravity. Now, what happens is that even though inflation is so successful, it has it faces a similar situation, which is that it has to have a singularity in its past. So kind of similar to the hot Big Bang. Now we should have a singularity to the past of inflation. Of course, the conventional wisdom is that at that singularity, the Planck scale physics or quantum gravity becomes important. It somehow tells us what should be the wave function of the universe. How do we emerge from that singularity? However, we can ask or wonder whether there is a semi-classical description in a similar way that inflation was a description of the origin of the hot Big Bang. And in fact, this question was also asked a long time ago by many authors. Perhaps the simplest scenario, simplest proposal is a no-boundary proposal of Rtle and Hawking, who say that the manifold that describes our universe, it has to have no boundary. So there has to be some Euclidean completion of this region. If this is supposed to describe the black side, it's supposed to describe the inflating universe. So it's inflation, the global, the future part of global de Sitter. Of course, then eventually it reheats and all of the usual stuff happens afterward. So the idea is that there will be some Euclidean part that caps it off, makes it a no boundary manifold. In fact, this proposal is very successful in giving us the right initial condition for fluctuations during inflation. It predicts the spectrum of fluctuations. However, it gives a wrong prediction for the scale of inflation, because it basically predicts that the scale of inflation should be the lowest possible value, meaning that if we also buy this prediction, it would predict that there is no inflation. So here we are asking about an alternative. The alternative is that to the path of inflation, we have eternal Minkowski spacetime, and this inflating region was produced by tunneling from that Minkowski spacetime. And so what I have done is to give some example that suggests that this is a possibility. It doesn't seem to be inconsistent to be a description of what happened in the past. Okay, so now I'm going to talk about a bit more about the technicalities. I don't know if the questions are supposed to be at the end, so I should continue, I guess. So there is a similar problem that was studied recently by Fu and Maroff, and that problem is to ask whether we can form an inflating bubble inside asymptotically ADS spacetime, and the question is formulated via Euclidean path integral. Can we do have a Euclidean path integral preparation of a state that has this bubble, inflating bubble? So these are some pictures from that paper. They basically answer negative to this question. But why is it similar to the question that I'm asking? It's similar because in whatever initial state which we want to have to eventually tunnel into this inflating region, that initial state can presumably be prepared via Euclidean path integral. So this is a natural, this is a general belief that we can prepare general initial states via Euclidean path integral. And then if we take the limit of ADS lengths going to infinity, that becomes locally like Minkowski spacetime. So the expectation is that the expectation is that if we solve this problem, effectively we also solve the problem of tunneling from asymptotically Minkowski space. There is, however, another. There is even a closer connection to this setup, which is my focus, which is if we consider the near horizon geometries of near extremal black holes. And this is a topic that has also attracted lots of attention in recent years. There has been a lot of progress on this. So we are considering, let's say we focus on 4 dimensions. We consider near extremal black holes, and the spherically symmetric black holes. And there are two. We want to consider 2 possibilities. One is a Schwarzschild de Sitter black hole. So remember we had we have a false vacuum and a true vacuum. So in the false vacuum, which would be de Sitter, we can have a Schwarzschild de Sitter black hole when f of r is given by this function. And then in the true vacuum, we can have a Reissner-Nordstrom black hole, a charged black hole. And now, why do I consider these geometries? Because if we consider this black hole solution and we go near the extremality, in the Schwarzschild de Sitter case, it would be the case in which the size of the horizon of the Schwarzschild black hole inside the Sitter becomes almost the same size as the Sitter horizon. In the Reissner-Nordstrom case, we have 2 inner and outer horizons. That would be the limit in which the 2 approach each other. In this limit, there is a nice simplification, which is that near the horizon we develop a long throat, and then the near horizon geometry becomes effectively 2-dimensional. So here I'm writing the metric. There will be the spherical part of the size of the sphere near the horizon becomes almost constant with a small fluctuation, which I call phi, and then there will be a 2-dimensional part. So we can reduce this 4-dimensional problem, assuming a spherical symmetry, we can reduce it to a 2-dimensional problem. And then the 2-dimensional problem is, again, a gravitational theory, but a much simpler gravitational theory called the Jakiv-Teitelbaum gravity, and with some matter fields that are coupled to it. So this problem of tunneling from Minkowski to the Sitter, if we want to do it do it in this near horizon geometry, it reduces to tunneling from a 2-dimensional ADS to a 2-dimensional de Sitter. I guess I forgot to say that if we consider this Reissner-Nordstrom solution and take this near extremity limit, then the near horizon geometry becomes ADS2 cross S2, which is the sphere. And then in the case of Schwarzschild de Sitter, it becomes DS2 cross S2. So the size of S2 or the sphere is this phi, 1 plus phi. And what we are considering is the tunneling from this near ADS2 to the DS2. Okay, so this is a major simplification of the problem. So then the mathematical formulation of the problem becomes the following. We have the Schwarzschild de Sitter solution. Now I have done analytic continuation to Euclidean. And if we consider this, so that we said Schwarzschild de Sitter in this near extremity limit becomes basically the DS2. DS2 rotates into a sphere, S2. there will be a phi solution. This is essentially the size of the other S2 factor, and this P is telling us how close we are to extremality. So if we are at the exact extremality limit, phi would be 0, because phi was the fluctuations of the size of the sphere. And then we have the Reissner-Nordstrom solution, the charged black hole solution. And then again, near the horizon, we have this ADS2 solution. Again, I rotated it to Euclidean. And then there is, which has this piece where A discusses how close we are to extremality, and this P0 tells us how the extremal radius of one geometry differs from the other. So these are all supposed to be a small parameter. In addition to that, we want to excite or Reissner-Nordstrom black hole to tunnel to the state. So in general, if we want to tunnel to a false vacuum, we need some excitation. We cannot sit in the vacuum and tunnel. So there has to be some excitation. This excitation here is modeled by some branes, because we want to preserve the spherical symmetry of the setup so that we can simplify. So there is a brane which, after this reduction to 2 dimension, becomes just a particle. So this is this red line. So brane has some tension which translates into some mass for this particle. And then there are the domain walls for domain walls between the ADS region, which is the asymptotic region, and the de Sitter region. So the whole setup is to find a solution where we have this geometry, and there are these parameters. So the question is there some choice of these parameters, the brane tension and domain wall tension, and these parameters of the background solutions, which gives us this following bound solution, Euclidean solution. Once we find this bound solution, then we can cut it at the moment of time symmetry and rotate it back to Lorentzian picture. So the Lorentzian setup is the following. We have two ADS2 regions in the left and the right. So these are supposed to be the near horizon geometries of charged black holes. So we really have two charged black holes, or really a Reissner-Nordstrom wormhole. So the two most of these charged black holes are connected inside via wormhole. That wormhole is excited via this brane. So maybe I should go actually to this slide. So this is a situation without the tunneling. We have these two asymptotic regions. These are supposed to be the two mouths of the wormholes that eventually open up and connect to the asymptotics, and then there is a brane in the middle, which is the model for the excitation. And then this brane decays into the domain walls, and so then the solution that we are interested in has this de Sitter region in the middle, and there is this domain wall. This domain walls fall in the inside the black hole horizon, but there is an inflating region in here. So this setup is all two-dimensional. The size of a sphere is approximately constant over this. However, as we move towards the boundaries, either here, this left and right, or to the future, then we expand. So here we have some inflating solution, and eventually the size of a sphere also expands, and the problem becomes 4-dimensional. So here we get a full, to the future, we get a full inflating solution, 4-dimensional inflating solution. Okay, so I'm running out of time. The next few slides are just the details of how one can find this solution. So the whole idea is to find there is some equation for this domain walls and the brains. There is a junction condition that says that there should be a continuity or some jump of this phi field across the brains and domain walls. So basically one can solve these the equations. And the whole point is that there is some choice of those parameters. I'm just skipping over this details. There is some choice of parameters for which there is a solution. So you get some effective potential that in Euclidean signature you go bounce back and forth between the turning points, and then at one of the turning points one can do the Wick rotation, and if it's done at this point, then the domain wall falls into the black hole horizon. Now with this two-dimensional setup, we can also try to estimate what is the probability for this process. And the idea is that in the saddle point approximation to gravitational path integral, we just need to compare the action for the bounce solution with the action without the bounce, with just the brain. And this difference, if we use a UV regulator, the UV here means the mass of these wormholes, which connect to the asymptotic Minkowski space. And so this 2D setup is just the interior of this wormhole when the size of the sphere is almost constant. So once we do some UV regulation, we find that the difference of the action is not too large. Too large meaning the entropy of the black hole. So it seems that there's a good chance that this process happens. Of course, it's exponentially suppressed, but it seems to be reliable since this difference is not too large. And finally, I should say a few words about the embedding of this setup in Minkowski space. So this setup required to start from a two-sided black or wormhole, a charged wormhole. So the question is, can we even have such a thing? And it seems that the answer is yes. There is, again, many years ago, about 30 years ago, there was this idea that you can pair produce them, like Schwinger pair production. We can pair produce them in large enough magnetic field. Recently, there has been some, I would say, even more interesting proposals of producing a traversable wormholes, a traversable wormhole using the negative Casimir energy. And once we have a traversable wormhole, then exciting it and making it non-traversable is trivial. So it seems that there are also constructions of the original geometry that we need to find this solution. So to summarize, I have proposed a solution that suggests it is possible to tunnel to the false vacuum and produce an inflating region inside the false vacuum and starting from true vacuum. This setup that I considered here is it produces this inflating region behind the horizon of a black hole. So it is causally disconnected from asymptotic Minkowski observers. However, and this is something which is under investigation right now, we can ask if we could do this tunneling inside the traversal wormhole, then this region would be for a while even accessible to the Minkowski observers. Of course, eventually it would be disconnected. Okay, I'll stop here. Thank you.
Okay, thank you very much, Mehrdad. It was very nice talk. So now it's time for questions. Please either write down, type your questions, or raise your hand in order to have your voice.
Okay, so there is a question by Ali Akbar. Do you have any prediction for the scale of inflation in this scenario? No, I don't have any prediction for the scale of inflation because well, I mean, it depends on the value of CC in the false vacuum, about which I didn't make any assumption.
Ali Akbar also has another question. What are parameters determine this scale, I think?
The parameter is so if you remember, I had this potential, this double well potential. The scale of inflation is determined by the CC, by the vacuum energy of the false vacuum. So this is a parameter of the model, and so far I haven't studied very realistic or many examples, but so far it seems that this is a parameter, so it can change. Of course, there are other consideration, whether you can actually make that potential from a UV scenario. But at this point, I don't care that much about that. I just postulate that there is a false vacuum and ask whether we can tunnel.
Okay, Ali Akbar asks another question before going to Hamed's question. Is it totally free? I don't know.
Is it totally free? Okay,
it seems that he's
I
now
imagine the question is that is it totally free to choose the scale of inflation?
It seems that Ali Akbar is satisfied now. Now we go to Hamed Shafai. Hello, I have a question. Is the brain in an RN system stable? Asymmetries can perturb the set.
So if the brain in the RN system is stable, well, essentially what I'm showing is that no, it is unstable. It decays into, there is a probability for it to decay into this inflating region. But perhaps maybe one related question that one could ask is that you might ask about a more detailed microscopic description of this brain, which for me was something that I put in by hand. And if you consider this double well potential, you can imagine that the brain and domain and I have reduced it to a two-dimensional setup. So these things can be thought of as the fundamental particle and the kink anti-kinks in this double well solution. So this if we didn't have this particular gravitational setup, what would happen was that the fundamental particle is stable because it's much lighter than the kink anti-kink configuration. So there is a coupling between them, but it is kinematically forbidden for the fundamental particle to decay. Now, what I have shown is that in this particular gravitational setup, this kinematically forbidden process can become kinematically allowed. A similar thing to think about is like a Schrödinger pair production. Or imagine if you have an axion that is light, but it is coupled to electron positron. So this process is kinematically forbidden if the axion is light. It's kinematically forbidden for axion to decay into electron positron. But if you have some large enough electric field, then the axion can decay into electron positron, because then the energy would be provided by this background field. So here the idea is similar. There is some excitation that normally wouldn't decay, but in this gravitational setup it can decay.
Okay, thank you. I think that now that's the time to go to the next speaker. Thank you, Mehrdad. Thank you very much.
Thank you.
Yeah, let's change the presentation, Priya.